Hey everyone, welcome back to the lab. In this video, we're going to be talking about Python Dataclasses, the best practices when using them, and then why you should really be using Python Dataclasses in your Python projects. This post originated on my blog, so I'll have a link to it in the description for HAMY.xyz. Now let's get into it. I prefer static types over dynamic types, as I believe it makes code more explicit and expressive, thus making software simpler to build and maintain long term. In my opinion, types are a simple scalable system, 3S, for managing complexity at scale. Now, this is always a very controversial opinion, and like everyone always fights about it, static over dynamic types. This is one of the few things I think I'm really bullish on in programming, because I've seen it go so wrong with dynamic types over the years. And my main argument for it is if you can't define the types going through your system, so the model of what the players are in your system, what the problem is, the solution and how it turns from, initial thing to solved thing, then you don't actually understand the domain, and therefore it's very unlikely your thing does what it's supposed to do well. I'm not saying it's impossible, but if you can't define those things, it feels like it's very unlikely. So that's my hot take. Fight me in the comments, especially if you're using dynamic types and you're really, on this side, let me know why. But yeah, that's what we'll start the post off as. Alas, you don't always get to choose what technologies you use in your day-to-day work. In the past 5 years and 3 companies of my software engineering career, Python has been a large component of our systems. Python is a dynamic language at its core, though its type annotations have gotten quite good recently. Yeah, this is totally true. Like, while I don't love dynamic languages, and Python's not my favorite, it's also not that bad, and I think is still the most popular, language used in the industry today. So I feel like a lot of people are probably in this boat with me, where you're just kind of forced into Python and you're trying to figure out how to make it suck less. But some examples of places I've used it. So worked at Instagram for 3.5 years. Basically, Instagram runs Python as their primary backend, which I think surprises a lot of people because, they've got like huge DAU, like 1 billion daily active users. And a lot of people think Python doesn't scale. Surprise, you can get pretty far with Python. You can read more about that and other weird things in Instagram's tech stack, like they don't use Git in this post. Reddit, worked there for like 5-ish months. And Reddit's primary backend monolith is also built with Python. And interestingly, they're running on 2.x. We'll talk about this a little bit more later in this post, but I always thought this was fascinating. And then finally, Rippling. That's a new company I started working at a few months ago, and their backend monolith is written entirely in Python. We'll probably talk more about their architecture like in another video soon, but I really like Rippling's architecture. It's kind of the architecture I like using for everything, the architecture I use for Cloud Seed, that kind of service-oriented architecture, but really service-oriented monoliths. Really enjoy that. Think it scales really well, and think the DevX is incredible. So a really good, simple scalable system for architectures. Anywho, this leads to the question we'll explore in this post. How can we wrangle complexity at scale in a dynamic language, Python? And so I think in this post we're gonna cover this like in multiple ways. First, like the wrangling complexity in dynamic languages, and then we'll also be mostly diving into kind of implementation specifics with Python. Cool. And so the answer is basically you should use types. Python's a dynamic language, but if you actually want to get explicitness and power and remove this complexity, you got to use types. And then further, data classes are a great tool to enhance these types, to enhance your code base throughout. All right, so Python allows types via annotations. They're not as powerful or strict as most static type languages, but they do move many errors to the build time, i.e. when you run your type checker, which achieves a lot of the value in terms of improving DevX speed and correctness. Thus, we can utilize these annotations to narrow the possibilities throughout our system, making our business logic more explicit, precise, and thus correct. And I think this is probably the biggest argument I have for static types, is that a lot of people say that static types are worse than dynamic types because dynamic types is easier to write things faster. But I actually think that's incorrect, because you might get the first thing out faster, but then you have all these other errors that'll happen down the road, like weird edge cases and runtime errors and stuff, that actually makes the total time to build a like robust thing longer. And then the basically overarching idea in the industry right now of how do you make the full cycle, this full, continuous improvement, continuous delivery cycle faster, is to move errors to the left. And what they mean by that is having less time between when it is implemented and when you catch it. And the fastest you can be is at build time. So I just built something and now I know it's immediately wrong. And you get that with static types because it's like, hey, this this type's wrong. Hey, this won't work. This will throw, all sorts of things like that. So it's almost like a prerequisite. In order to get those things, you have to have these types defined. All right, now you might say that a large emphasis on types is non-Pythonic. Pythonistas are going to hate me, and gets away from the dynamic roots power of the language. You might be right, but I really don't care. I believe the goal of any programming language or ecosystem is to be a good, useful tool for accomplishing your goals, largely building 3S, Simple Scalable Systems, to solve problems. In my experience, non-explicit, non-precise languages, dynamic, always become a bottleneck at scale because the mental overhead required to understand what's going on increases exponentially. Yeah, I'm a very dense writer, I'm realizing, so I'll try to dive into some of this stuff. Yeah, Pythonic and Pythonistas, I basically hate when any language does this. They're like, it's not the X way of doing things. It doesn't matter to me what the tradition is in a language. What matters to me is we're aiming for better code, right? So if your tradition happens to be actually better code, then that's fine. I'm all for it. But if you ever say the reason we're doing this is because like tradition or because like this is, I don't know, more within the values of like the creator, it's like, who cares? Like they might be wrong. And a lot of times when I see people using this as an explanation of something, it's because it doesn't actually fit the values of what we're trying to achieve. And so it actually is more often wrong than right is my posit. Especially for Pythonistas, man, this Pythonic stuff you'll see with like these weird constructs and like lambdas and stuff. Like I get it. You think it's simple, but simple often leads to complexity and therefore it's not simple. We'll get into some examples of this in a second. And then, yeah, I think we already talked about this where dynamic languages end up becoming a bottleneck at scale. And that reason really is just because it's hard to figure out what's going wrong. It's like, the way I always think about this is like you're doing dynamic languages. So it's like, if you have a bunch of electronics and you have a bunch of chords, obviously, you have two ways of doing this, right? Like you can basically have some chord management where you like, well, I guess I'll say, let's start with like, there is no chord management. So you just have like all these wires everywhere. And it's like your TV, your receiver, your Xbox, your, I don't know, Google Cast thing, like all this stuff is back there and it's powering all this sorts of stuff. The next time that you need, like something's broken or you're swapping out one of these devices, you're going to have a nightmare of trying to figure out what cord goes where, untangling the things. And then because there's no system of like how they're organized to even put it in and like get the chords in and stuff, it's just like going to be a mess. That is dynamic typing. Static typing is like, okay, you know, you don't have to do whatever's on Reddit and like these crazy color-coded things or anything like that, but you can do more than letting it become a knot of chords. You can like take the extra of each chord and like tie it up so that's all in a bundle. And that's already like 80% better for like, I don't know, 10, 20% extra work. And code is basically like that. Like at scale, when you've got thousands of files and you got hundreds of engineers on the thing, dynamic is like everyone is adding chords and removing chords and stuff, and they have no idea what they're unplugging or, you know, what could be at risk. Static types at least helps you manage that thing. You know, it doesn't prevent all these things to start with, but it at least manages the chord. And, you know, I've basically seen this bottleneck happen at each of my past companies and seen them have to go through this very painful process of unwinding all those like tangled chords. So, you know, at Instagram, you know, we started as an untyped Python monolith that, you know, actually it worked for Instagram for, you know, a lot of years. But at scale, it just didn't work. And so they went through, I don't know, a year plus process of typing all of Python with the annotations and honestly moving a lot of the large and complex workloads that were doing like a lot of CPU things or maybe like the types are hard or whatever to a different monolith using Hackling, which has a bit more powerful of a type system. Reddit was interesting to me because they had run as a Python monolith for over a decade. And this worked when they only had like 3 engineers basically who were like keeping it up over the decade. And it worked because they all had so much shared context, right? They'd been working on it for so long that they could kind of understand what chords went where and like, you know, stuff like that. But by the time I joined and they were going through a scale up phase, they had like hired hundreds of engineers and it was so hard to untangle these chords, all these like logic things that they basically called bankruptcy on their monolith. It was running, you know, Python 2. They said it's not even worth trying to upgrade to Python 3. Instead, we're going to say nobody can make any changes to this thing because we don't know what's going to work or what's going to break. And we're going to rewrite everything into Golang microservices to try and prevent this like, you know, tangle of chords from ever happening again. At Rippling, where I just joined, you know, it's a untyped Python monolith for the back end, and they're slowly moving to fully typed Python. There are a lot of engineers here, and they've gotten pretty far without the Python monolith, but they're still early stage. stage. So I'm excited to see that we're, going to fully typed so soon. All right, in the rest of this post, we're going to explore how to best leverage data classes to make your code more precise, explicit, and easier to understand. I do have a replit, which we'll be playing around with as well as we go, and I'll have that linked in the description as well. Okay, Python data classes. The generic term for the pattern Python's data class fills is called a record. Yeah, and a lot of languages like F#, C#, they just call this records, but a lot of languages have like a weird name for this thing as well. Records are typically lean data only structures containing a fixed set of named typed fields. And so here's an example of this. My website doesn't have the greatest or like really any highlighting, so I'll probably show you this in Replit as well. All right, so here I am in Replit, and I've got a bunch of examples. I'm just going to run this to show that it's actually running this code that I'm showing you. And here's example one. So it's just simple data classes, and basically what I'm trying to show you is like different ways to model a temperature in unit pairs, because like 50 degrees depends if it's Fahrenheit, Celsius, example like that. So, we're just going to define unit, just use a simple enum, Celsius, Fahrenheit, okay? And then we're going to have a data class temperature, and this is what it looks like. So, import data classes or data class from data classes, and then you basically just set some fields and you give it a type, and this is going to give you an implicit instructor or constructor in here. And this is why it's useful. So in Python, if you're just going Pythonic, you might do a full class, but often for like small amount of parameters, or even I've seen it for more parameters, but like there's no logic involved, people will just go for straight tuples for like 2, 3, 4 params. And this is okay and it works, but like I hate this syntax because oftentimes it's not going to be, the usage of this thing is not going to be as like close to where it was set. And so you actually have to dig to figure out what is this tuple, and like where is it coming from? And a lot of times this will be coming from like, let's say, I don't know, some func returning tuple, right? And it's going to return like something like and then bool, where oftentimes the bool is like whether this like was successful or not. What is this? And like you can sometimes figure out what these values might represent based on the function, but like you don't have any way of knowing exactly which value is supposed to represent what. And so tuples fine, but again, at scale, this kind of untyped nonsense turns into like a lot of complexity. Okay, so how do we fix this with data classes? Basically, since we have this data class, we can create this, and now we can say like, it's a named tuple, right? We know what every field is supposed to be, assuming it's set correctly, and so we can use them here. And, we print them out, and Python pretty prints, so we can see it's 50-50. Okay, so why they're useful? Yeah, we often want to group data. We want that data to be explicit, easy to understand, and hard to get wrong. And we can use fields and types to constrain, the possibilities here, and thus lower the mental overhead that we have to keep in our brains. Tuples quickly become cumbersome, usually at 3+ values. Yeah, kind of like I just showed you, like it's hard to trace where it's coming from. For maybe 2 values, it's okay, but as soon as we get to 3, it's like, this feels bad. Data classes are great lightweight constructs for explicitly constraining possibilities and lowering mental overhead. Yep, and so basically as a rule of thumb, if you're considering returning or passing around a group of multiple values and you might consider a tuple, I would recommend at least considering a data class. Sometimes a tuple is fine, but in most cases, I would say you really want a data class. You really want this named tuple, if you will. Okay, immutable data classes. So a common refrain in programming is that mutability is the root of all evil, or at least a major cause of a lot of complex, hard to maintain, and fragile software. But the truth is that all software must contain mutability somewhere, otherwise it's probably not useful. So the real takeaway is that poorly constrained mutability makes systems incredibly hard to reason about and thus to build, so constrain your mutability. Vanilla data classes are mutable out of the box. This makes sense as Python is default mutable as well, so at least it's consistent. But for a good 3S system, we almost never want this as it's so easy to get wrong. Instead, we want to build a pit of success by constraining mutability via enforcing mutability. Note that everything that I'm talking about of like constraining possibilities, constraining edge cases is really going towards this idea of a pit of success. It's not that we don't trust our developers, it's that we know that all humans make mistakes. When you think about all of this stuff rationally and how do you fix it as a system, it's never to blame a given developer. It's like the reason that this happened was actually because our system is so complex that they were forced into this. It's like, it wasn't that they were not being careful, it was that there was glass on the floor and they just walked and assumed there wasn't glass on the floor and they cut their foot. That's not their fault. There shouldn't have been glass on the floor. We can make our data classes immutable by utilizing the frozen parameter. This will throw if anyone tries to mutate the object at runtime. And so this is how most dynamic languages show errors. So as we're talking about moving to the left, most dynamic languages can only catch things at runtime, which is either in a test or usually in prod, in my experience. And most type checkers can pick up on this and warn error at build time, thus making more error cases visible earlier in the dev cycle. Now, most static type systems, if they have a good enough type system, and I will say most static languages don't have a good enough type system. Look at F# TypeScript for good examples of good type systems that can do this. The types are so good and explicit that it's hard to get something totally wrong at build time. Because things might still go wrong, but at build time you catch most things, like 80-90% of things that could go wrong. And because you can figure this out like in the editor, as soon as you make the change, it's much faster to go and fix it than to wait till it's prod or your tests run or whatever. Okay, example 2. So let's go back to our replit, and now we're down here at example 2. I'll run it again to show you what's going on. Oh, and then I have to uncomment this. Okay, so what are we doing here? Basically, I've got a data class. This is just mutable because it's just like a normal one. And then I'm just have this function that's going to take the mutable data class and it's just going to mutate it. That's all it's doing. Going to return none. And we can see that we've got our mutable example. It starts off as 1, and then we are able to mutate it. Now, let me run this uncommented code. And then after the mutable DC, we see we are trying to do the immutable DC here. We're creating our data class exactly the same, but now we're adding this frozen attribute. We now have the same thing, bad mutation, but it's blocked, takes in the immutable. And we can see that even in our editor, it's showing us that like, hey, you can't do this. So this is how we're getting the build time errors. But of course, Python, because it's dynamic at heart, we can still actually build and run this, even though it has, what would be compile time errors in other languages. But when we run it, we at least get this very clear runtime error, showing us that, hey, you can't do that. So I'll comment this out again so we can run the rest of it without erroring and come back here. Okay, so now you might be saying, okay, this makes sense, but this example is contrived. No one would ever write code that mutates the passed in parameter. And I'd say, ho ho, very funny. Tell that to pass me who spent a whole day last week debugging weird values to find that params were being mutated 5 levels down. The interesting thing with Python is this is actually so common, but it's kind of implicit. Although in Python, they do make it a little explicit. Like, let me show you an example. So, okay, how many times have you seen something like this? Class, my class. We've got, an int, which is like an int or something like this. And now you've got something like this. All right, def do something. And what this thing does, actually, usually it does something like this. So we'll say an int, and then it's gonna say like, let's say 1, return. How many times have you seen this? Probably a lot. There's definitely a lot in the code bases I've seen because this is like kind of object-oriented programming. Guess what this is? Guess what this is? You are changing your parameter, and you can say that like this is how you do object-oriented programming. This is how you do side effects, whatever. But this is the same as doing this here. It's just a little bit more implicit. So yeah, don't tell me that people aren't doing nested side effects, changing the parameters passed in. It happens all the time. Okay, I'm done fighting with hypothetical people. Okay, do yourself a favor and build the pit of success to make it impossible to do bad things. Again, this is what we're trying to do. We want a pit of success. We want to stop the bad things from happening on accident before they happen. All right, explicit data classes. So the whole idea of types and data classes is to make things explicit. Data classes certainly help over alternatives like unnamed tuples, but will still commonly run into cases where they become similarly implicit with high mental overhead. I've most commonly seen this happen when we are modeling a record with many values, typically 3+, which is again why I recommend when you have 3+ to start making your things more explicit. Data classes come with a built-in constructor that's based on position. It's an order-based constructor. When we have less than 3 values, this can be sufficient as it's not too hard to remember what the properties are via order and type. However, as soon as we get over that amount or have several fields with the same types, this can become exceedingly confusing and thus lead to a lot of mental overhead. It's often easy to forget what field value means, and that means it's often easy to set the wrong thing to the wrong field to the wrong value. Yeah, I think I said the same thing multiple times here, but whatever. Another insidious issue with order-based constructors is if someone refactors the order of the properties, it changes the order of the constructor parameters. This could mean a lot of fields are now being initialized with the wrong values, and if you don't have type errors, i.e. the swap fields are compatible types, or tests covering this, you may never know till runtime. So what I'm saying here is, and we'll show this answer in a second, but like, okay, we see this, no keyword DC, and we're creating it here. This is like 1,000, 1,200, 1,100 maps to the same things. Now, if I change this to say, go up here, guess what? No type error because they're all the same types, but now each one of these is being assigned to the wrong field just because someone decided to come and refactor this order based on, I don't know, something that made it go to the top. And now if you've used data classes a lot, like you're like probably won't do this and you'll stop people from doing it, but this is that thing where we're trying to build a pit of success and this is an obvious failure case that like could happen. Yep, and this can can mean a lot of fields are now being initialized with the wrong values. And if you don't have type errors, like I showed you, int to int, it's no type error, not going to show you anything, or tests. So like you're never going to know this till runtime. So yeah, you need tests, which I guess is technically runtime, or you're going to catch this in prod. And like, you know, it's just bad. Like we want to make bad things impossible to happen. And this is like a clear potential of a bad thing happening. Okay, so how do we solve this? So the easiest way I found to solve this is to utilize the keyword only flag, which makes it so that every field value must be explicitly set on the data class. Of course, you can still set a field value incorrectly, but at least you're forced to read the field you're setting before doing so. This solves both problems. It's easy to read what field is set to what value, and it's harder to set the wrong field, the wrong value. And so here's that example, our explicit data classes, and kind of like I showed, we've got no keyword DC, so it's got frozen on it, but that's it. So we've got these things, and now we're going to set them in order. And what I'm trying to showcase here is that like you're very rarely going to see this case where you create it is very similar or very close to where you're using this type. And maybe I can make this bigger. You're often actually going to see it like this, where it's like you see the values going into the DC, but you're not right next to the definition. And so yeah, you can use the type hints to kind of help, but like you're just glancing at these things. All of this looks fine. But actually one of this is being set wrong. And it's this fourth one here, but like at a glance, it's very hard to see. Even if you're typing these out, it's very easy to get this thing wrong. And so you'll often see this, like, you know, the DC is used way somewhere else in a different file. So you don't have the definition like top of mind. And so it's very easy to set this wrong. Or I often actually see DCs. I use them a lot for test cases. So we get some typing in our test cases. And so you'll get like these long, often like 6, 7 parameter data classes that are basically representing everything about this test case that we want to test, initialize, and assert on. And so when you've got like 10 test cases by 7 parameters, it's so easy to get like a few int values or int fields mixed up. So which one's wrong? Yeah, it's this fourth one. It's just set different than the other ones, but basically impossible to see. All right, so what can we do about this? We can do keyword only. And what this is going to do is it's not going to let us set things just implicitly. We actually have to say this stuff together. And so this helps a lot because, like, you know, again, we're in the middle of a list. Well, if we're ever confused about what something is, we just check. It's like, oh, this must be 1,000. Oh, this must be 1,200. And so you can still set things wrong. Like here, you know, our fourth case is wrong again. But by looking at them, it's so much easier to see like, oh, this is the field, this is the value. That seems wrong. And because we're setting by keyword, we don't have that problem of like if someone decides to change the ordering, like I moved 1,200 up here, it doesn't matter because each of these is explicitly set. So now we're not tied implicitly to the ordering of this. All right, next. When I get to choose my tech stack, I typically reach for languages with great ergonomics for writing explicit code. Currently, F# and TypeScript are my go-tos. Talked about this a lot. Check out my other videos. But you don't always get to choose your stack, so hopefully this helps you wrangle the implicit complexity in your own Python project. That's it for this video. If you're interested in learning more about F# or any of these guys, I'll have these linked in the description and probably in a card somewhere over here. Thanks for watching, and I'll see you in the next one.